Good morning. Today we will see the experiment on Newton's rings. Newton's rings works on the principle of interference. Interference, as we know, when two or more light waves overlap, the intensity modification takes place. That phenomenon is called as the interference. So when the waves overlap, if the path difference between the waves delta is equal to an integral multiple of wavelength lambda, delta equal to n lambda, will get brightness. Same way, if the path difference is equal to 2n plus 1 lambda by 2, we'll get darkness. So these are the conditions for constructive. Brightness is constructive interference, darkness represents destructive interference. So if I take the path difference gradually increasing from 0 onwards, so when n is 0, that is when the path difference is becoming 0, I'll be getting this condition satisfied. So n is 0, path difference 0, so I'll be getting a brightness. Again, when n becomes, it's an integer, n can take values 1, 2, 3 like that. So if 0 also possible, 0, 1, 2, 3 like that, any number, integer. So if lambda becomes, so a specific value, when n becomes 1, n becoming 1, we'll be getting the path difference delta, this is increasing to n lambda. So n is 1 lambda delta. This equation satisfies. Again we'll be getting brightness. When n is 2, we'll be getting again brightness. So these all represent, so lambda, that is lambda 0, lambda, 2 lambda, 3 lambda, all these things will be getting brightness. Now if I go for this n is equal to 0, if I put, I'll be getting the path difference equal to lambda by 2. It comes in between. So you'll be getting a dark part here. Same way n1, so 3 lambda by 2. It comes in between this. Next 5 lambda by 2, 7 lambda by 2. All in between I'll be getting darkness. That means if I form an interference pattern with a specific wavelength, that is, there should be only single wavelength. So the light what we use for interference should be a monochromatic source of light. Monochromatic means it should give only single wavelength. Sodium is nearly monochromatic because it gives two wavelengths, 5890 angstrom and 5896 angstrom. So usually we will take the average as the wavelength of the sodium. This much difference is not there. So if we use a monochromatic source of light, we will be getting an interference pattern alternatively bright and dark. Darkness and brightness will come alternately. Almost you can see the pattern will be like this. Now in this case, to make the path difference between the rays, what we are using is like this, a setup like this. A plono-convex lens. Plono-convex lens means one surface of the lens will be plane, other surface will be convex. This is called as a plono-convex lens. And below we are keeping a plain glass plate like this. This is the setup. So our experiment here is to find out the radius of curvature of the plono-convex lens. Radius of curvature. So we will be using a monochromatic source with a known wavelength. So in this case we will take the wavelength of the sodium light as 5893 angstrom. So lambda is taken as 5893. And here when you are keeping the lens, plono-convex lens, with the curved surface touching the glass plate, exactly at the middle point of the lens, it will be touching the glass plate. So the air film thickness there is 0. And outward, as we can see here, the gap increases and it is uniformly increasing in all directions. So if I take some distance here the air film thickness in this position will be same as the air film thickness to the other side, to the same extent this side. Same way, if I see from top, throughout the circumference of a circle, if I draw a circle on the surface of the lens, throughout the circumference of the circle will be getting the same thickness continuing. So, depending on the thickness, path difference will be generated. So, at the center, path difference is 0. So, because of reflection, there is one lambda by 2 added. So, path difference condition at the center, this becomes the condition for path difference is this plus lambda by 2. So, you will be getting the center as a dark point. You will be getting a dark spot at the center. Then again, as we go outward, path difference increases. When this increases to next condition, you will be getting a bright ring. Then you will get again a dark ring. Then another bright, again dark. This way we will be getting alternate dark and bright rings. This is called as the Newton's rings. We are getting large number of alternate, very closely spaced rings starting from a dark center. So this I can count as the first ring. This is the second, third, fourth, fifth, like that. I can put the order n, 1, 2, 3, 4. So this we have lot of rings. So we have the setup like this. This glass plate. Over the glass plate, I'll be keeping the plono-convex like this. A small gap will be produced in between. If I keep it reverse, there is no gap, small gap. This will be kept inside this array. Now in front of that, the lens is there. Lens will focus. So the sodium vapor lamp, if I keep here, this lens comes in front of us. So if the source is kept at the focal point, the radiations coming here in this direction, so it will be coming in this direction, so that can be made perfectly parallel. So rays will become parallel, and these rays are allowed to fall on a glass plate which will be kept at 45 degree like this, inclined glass plate, and below this will be keeping this lens setup, glass plate over that plono-convex lens placed like this. Now these rays, after falling on the surface of this glass plate, will be bending down and falling normally on this arrangement. This. After falling on that, if I enlarge the spacing like this, so I have a air gap here. The ray which is falling here, a part of the ray will be reflected because there is a medium difference. Remaining ray travels into the air medium. This medium is filled with the air, and at the bottom part of the air medium, again the ray reflects. So you are having an air film. From the top of the air film, one part of the ray is reflected. From the bottom of the air film, another part is reflected. Since this lens is with a large radius of curvature, the air gap formed will be very, very thin. So this we can count as a thin film interference. So when the air film is very thin, these two rays will be overlapping and they will be almost coming in the same direction above. They will be overlapping. When they overlap, we will be getting some points, the constructive interference condition will be satisfied. Some other points, the destructive interference condition will be satisfied. So, we will be getting this type of rings formed. Newton's rings can be formed. So, here we have the arrangement. This instrument you call as the travelling microscope. So, to see these, so the reflected rays will be coming like this and it will be coming up. And to see the rings, we will use a travelling microscope just above this travelling microscope. So, looking through the travelling microscope, we will be able to see this type of rings. To focus the rings, what we have to do is, telescope should be correctly focused towards the center of the lens system first, center of the lens. Then the inclined glass plate should be kept nearly at 45 degree. You can turn the plane of the glass plate and you can keep it almost at 45 degree. And the instrument or the setup should be in front of the source so that light falls properly on this lens setup. So now you will be getting this way light falling on the lens. After reflection from this inclined glass plate, light rays will be falling normally on this, and after interference you will be able to see the ring system through this telescope. If it is not clearly seen, the focusing screw of the telescope has to be adjusted and you will be able to see the ring system. In this traveling microscope, tangential screws are there. 2 tangential screws are provided. You can move this forward using this or left and right using this. So we are going to take the diameter. So in this case, when the rings are formed, the diameter of any ring, you can write, say if I write the equation for the radius of a specific ring R, nth ring, dark or bright, will be equal to root of n r lambda. R is the radius of curvature of this plano-convex lens. N is the order in the sense this I can say the first ring, this is second ring, third ring, fourth ring, like that, order of the ring. Lambda is that wavelength of that monochromatic source. Now this I can write Rn square, radius square of the nth ring is now nr lambda. If I go for the diameters, dn squared by 4, Rn squared I can write as dn squared by 4, this is nr lambda, or dn squared can write as 4nr lambda. Same way, if I go for another ring, say I name it as dm, so dm squared I can write as, only change comes in this order, mr lambda. Now if I take the difference between these two, I will be getting dm squared minus dn squared as, here 4r lambda constant, so 4r lambda into m minus n. So radius of curvature, if I want, I can write the equation for radius of curvature as dm squared minus dn squared by 4 into m minus n lambda. So to find out the radius of curvature, what we have to do is, we will have to take one pair of rings, any two. Suppose if I take 10th ring and 4th ring, then I am maintaining a difference of m minus n of 6. Like that, any number of rings I can go for. So I have to find out what is the difference between the diameter squares. So wavelength is known, so using that we can easily calculate the radius of curvature. Now to measure the diameter, what we will have to do is, so we can go for a tabular column, something like this, for inch number. To get more accurate value, number of trial has to be increased. So we can start from say 12. So if this way, if I see the rings, I can go to the 12th ring. So what I have to do is, initially I will be setting the crosswire like this, exactly at the center of the ring system. Counting the rings, I can move towards, for moving the ring, I can rotate this, slowly I can rotate this. When I rotate this, I can move the rings towards one side. First I will bring it to here, count it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I want to start from 12, I will go up to 13. Up to 13th ring I have to move. So in this direction I am moving. Now I will change the direction, turn it in the opposite direction and come to the 12th ring, tangentially to the 12th ring, this way. So why I am going up to the 13 is, when I move in this direction and for other rings, if I change the direction, there is a backlash error coming. To avoid the backlash error, if you want to take the reading from 12th ring, go up to 13, change the direction and make it tangential to the 12th. So when your crosswire is tangential to the 12th ring, you can go for the readings. Now to take the readings, what you have to do is, you can see here the main scale. Main scale is here. In this main scale, 1 centimeter is divided into 10 divisions. So 2 to 3, 1 centimeter is divided as 10 divisions. So here, 1 division in the main scale now becomes 1 centimeter by 10. That is 0.1 centimeter. That is the value of 1 division. This is the head scale. If you rotate the head scale, you can see markings are done. It's a drum. So starting from 0, 10, 20 like that, 100 divisions are there. So when I start from 0 and come back to 0, 1 rotation is over. When I complete 1 rotation on the head scale, here on this scale, which we can call as the pitch scale, similar to the screw gauge, here there will be a change of 1 division. Distance moved will be 1 division. So for exactly counting that, you can make 5 rotations. See how much distance it moves. Usually it will be moving 5 divisions. So distance moved by number of rotation will give you the pitch. So first we will calculate what is the pitch. Pitch in this case will be 0.1. Distance moved by number of rotation. And head scale is having 100 divisions. So least count of the instrument is pitch divided by total number of head scale divisions. So in this case it is 0.1 by 100 divisions are there on the head scale, 100, 0.001 centimeter. This is the least count. Now to take the readings, suppose if this position I want to take the reading. So I have set the ring crosswire to the 12th ring. So at the 12th ring position, 0, this 0 I will see on the pitch scale 0. 0 is now between 2.8 and 2.9. On the pitch scale I can see the 0 is lying between 2.8 and 2.9, something like this. 0 is there, this side I am getting 2.8, this side I am getting 2.9. So the completed readings I can take as the pitch scale. So in this case I will take 2.8 as the PSR. So I will write here 2.80. Now at the same position, if I note this head scale 0, that head scale 0 has crossed 87. It is between, in this drum, it is 80, it is between 87 and 88. It is something like it. So I will take the head scale reading as 87, completed reading. Now if I multiply this head scale reading by the least count, 0.001, and add it with the pitch scale, I will be getting the total reading as 2.887. So 3 decimals, correctly you should write the reading. So this total reading I will write it as 2.887. This is for the left side of the 12th ring. Same way, now if I slowly move it, I can bring it to 10th one. To keep a small difference, we are moving alternate rings. So leaving 11th ring, now we can come to the 10th ring. Make it tangential to the 10th ring. So definitely the reading will change. The new reading will be writing here. You will be getting another. Same way, we will take the reading for 8th ring, 6th ring, 4th ring and 2nd ring. So one side is over. Starting from 12, 12, 10, 8, 6, 4, 2. Means you will be reaching up to this point. Left side readings are over. Again we will move in the same direction, cross the center, come to the right side of the same 2nd ring, right side. So observations will be taken now in this case. 2nd ring, right side readings. Then we will go to 4th, 6th, 8, 10, 12. So we are getting readings corresponding to the left side and right side of 12, 10, 8, 6, 4 and 2, 2nd ring. These readings if you use here, so total reading on the left side, total reading on the right side. These two reading difference. So for a specific ring, if I take this as the 12th ring left side I have a reading, right side I have another reading. This difference will give me the diameter. This is the diameter. So left and right side reading difference I can note as the diameter. Same way I will take the diameter for measure, find out the diameter for all 12, 10, 8, and for easy calculation I will split this way, 6, 4, 2 I will write on the other side. So what I am getting is here, this I will note as dm, this I will note as the dn. So square of the diameters I can calculate. Then here I will go for, with a m minus n difference of 6, I can take 12th diameter square minus 6th diameter square as dm squared minus dn. Same way, same m minus n I can get even for dm squared 10 minus dm squared 4. Same way, dm squared, d is d squared 8 minus d squared 2. So 3 differences I will be getting. These 3 differences should be very close to each other. Mean of this I can count as the d squared m minus d squared. Same value. Since we are doing these things, the least count is in centimeter, your diameter squares will be in centimeter square. You can convert this into meter square. So this value into 10 to the power minus 4, and that same value you can use in this equation. So numerator you are getting from this final value 4, m minus n we are kept as 6, and lambda is the wavelength of the light, which will be given 5893 angstrom. Using this, the radius of curvature of the planar convex lens can be calculated.